Going to be taking a look at some advanced TypeScript types. I'm going to be going over this really cool post written by Gal Schlesinger. What he's basically done is shown how you can implement the classic FizzBuzz algorithm in TypeScript using types only with absolutely no runtime. This is really cool and it shows us some of the flexibility and power of the TypeScript type system. So I'm basically going to re-implement this and explain in detail how it all works. So let's go ahead and jump into it. The goal is to create a FizzBuzz using types only. If you haven't seen FizzBuzz, just pause the video and read this here. Basically, this is going to be the goal on line 10. We'd like to be able to write a type such that the definition is 1, 2, fizz 4, buzz fizz, and so on and so forth. You can see a very simple implementation right here in JavaScript. All it does is a for loop from I equaling 0 all the way up to n, and it checks if the number is divisible by 15. If it is, it logs FizzBuzz, 3 for fizz, and 5 for buzz. Otherwise, it's just going to log the number. This is going to be problematic in TypeScript's type system for a number of reasons. Firstly, TypeScript's type system doesn't have any concept of numbers. So for example, you cannot have a 1 type. You can have a number type, but this is very generic and includes the entire set of numbers, which is not really what we want here. So we're going to have to define our own very simple number system. There's also no way to do a for loop, so we're going to have to find a workaround for that. And there's also no basic math operations, so we're going to have to build our own modulus operator from first principles. Let's go ahead and get started by defining our number system. We are going to constrain ourselves to the question here. So it says from n to some number. We're going to go up to 16. So our entire type system or our number system is only going to have numbers from 1 to 16. Anything outside of 1 to 16 is going to be an invalid number. I'm going to define a type for that right now called nan, and that is going to be an invalid number. We're also going to have one type which is going to kick off our number system. That's going to be the 0 type, and that's going to be equal to 0. You might think, okay, let's make the rest of the types 1, 2, 3. This is not going to work, however. As a human, we implicitly know that 0 and 1 are related. 0 comes first and then 1. However, TypeScript has no way of knowing this. For all intensive purposes, this may as well be some random junk, and there's no relationship between these two numbers. We need some way to relate these two so we're able to perform those mathematical operations. What we're going to do is define a new type. It's going to be called increment. It's going to take a generic parameter of n, and it's going to increment this by 1. We're going to represent an increment by just passing in the value and saying +1. Again, this string is just a label. It could just be some junk, but this is going to give us a nice human readable output, or at least a kind of human readable output for now. So now that we have this, we're actually able to have a bit more of a meaningful number system. Let's go ahead and redefine our number here of 1, which is going to be not invalid, it's going to be increment, and we're going to increment 0. So we're going to say that 1 is the value of the function increment with applied to the value of 0, or the type of 0. What this means is that we could create a type of 2 as well. We might just say increment, and then we're going to call increment again and pass in 0. And we can see that 2 is offset by 2 increments from the base number of 0. This is obviously not very ergonomic to continually type increment over and over again, but we do know that increment 0 is equal to 1. So what I can do is delete this inner type and replace it with 1. And this makes sense. It's very readable from a human perspective. Again, these labels could be anything. I'm just choosing numbers to make it readable. But the point here is we now have a relationship between these numbers. 0 is directly related to 1 via this increment function. Let's go ahead and create a macro to create the rest of these. So we're going to have 2, which is just going to be increment 1. And we're going to repeat this 14 more times. So now we have 16 numbers. And this is a pretty good type system to work with. Anything outside of this, so if you increment 16, you're going to get a nan, an invalid number. And if you decrement 0, you're also going to get an invalid number. We have a way to go up, and we need some way now to go down, and that's going to let us implement subtract and eventually implement the modulus operator. Before we do that, however, we need some way to test everything to make sure it is working. We're going to write the simplest test framework ever. It's going to be a single type, and we're going to call this type equal. It's going to have a as the first parameter, and it's going to say b extends a for the second parameter. And we're just going to assign this to some random string. Okay seems fine to me. This does say extends, but what you need to do is think of this as equals. And I'm just going to explain how this works with TypeScript really quickly. So let's say we have an interface called foo. This is going to have a single property of ID, which is a number. We may have another interface of, let's say, bar, and this one is going to be an ID of number. We're also going to have an additional property here. The name is going to be a string. Now let's go ahead and create a function. I'm going to create a function called q. It's going to take a value of our foo type. So I'm going to say it should take a foo type, and to compile, this must receive a foo type as the first argument. If I go ahead now and create a bar type, not a foo type, a bar type, we're going to give this an ID of 1, and it's going to have a name of, let's say, name. And if we go ahead and call q and pass in our bar type, this is actually going to compile. The reason this is compiling is because we're using interfaces here, and the foo interface says that the value passed in here, the foo value must implement the minimum foo interface, which is just an ID. Bar fully does this, it implements ID, it also has a name, which I don't really care about here, but the fact that it has all the values for foo means it is working correctly. What we could also do here is delete the ID, and we could say that bar extends foo. And this means that bar does everything foo does, and it also does extra things, such as the name here. Although we don't really care about the extra things here, we just care about the fact that B is equivalent to A, and that's going to let us write a very minimal assertion. Just to show you how this works, I could jump down here and write a test. Let's create a new type. I'm going to call this one test. It's going to contain an array of our test cases, and we're going to say that foo is equal to bar. Based on our current equal function, it is equal. Bar implements everything that foo implements, so this is going to work just fine. If we pass in something else like A is equal to B, we know that this is not true at all. A is not equal to B. B does not implement A, and this is going to fail. And this is what we're going to use to test our system out. Now that we've seen how extends works, let's go ahead and actually write a new function. We currently have increment, which is good. We need to have the opposite direction, decrement. So we're going to go from the number and go down. Let's go ahead and implement that right now. I'm going to have a type called decrement. It's going to take a generic parameter of n, and this is going to use the infer type, which I'm going to explain in just a moment. We're going to say that n extends our value of increment such that we can infer the inner value of d. Let's go ahead and just make this compile, and then I'm going to explain this one. So we're going to say that we can infer this, or we'd like to try and infer it. If we can, we're going to return the d value. If we can't, it means we've decremented outside of our number system. We're going to return nan and not a number. So in practice, let's go ahead and actually write this and see what this might mean. I'm going to create a new variable here called result. It's going to be equal to decrement, not that, it's going to be equal to decrement, and we're going to decrement 4, and this should give us the value of 3. What we're saying here is there is some value in our system that satisfies this equation, n extends increment infer d. Remember, we're saying that extends is very similar to equal here, so we're saying that basically n is equal to some value of increment where we can infer this inner value here. Let's go ahead and take a look at the universe we've defined and see if anything fits this equation. We know that in this case, n is equal to 4, and if we look at those equations we have here, we're saying that the type of 4 is equal to increment with the inner value of 3. So it's going to infer this inner value with a question marks here and replace this one with 3 to make this equation true. We've managed to infer the inner value. Based on that, we have got an inferred value of d, so we're going to return d. If there is a case where we can't infer the value, we're going to return nan, and we're going to see what case that is in just a moment. So let's go ahead and actually write our test case. I'm going to create a new type called test that's going to contain our array of tests, and we're going to say that decrementing, let's say 4, should give us the value of 3, and this is going to pass. We have no compilation error. If we were to make an incorrect case, like 14 minus 3 should be, we should say decrement 13 is equal to 3. Obviously this is not correct. Decrement 13 is equal to 12, and that would now pass. If we try and go outside the constraints of our world, for example, decrement less than 0, we're going to get an invalid number. This is the only case it is going to pass because that is correct. There is no value less than 0, so we're going to say it is nan, and that is going to do exactly what it should be doing. So now we've managed to implement increment and decrement with a very rudimentary number system. Why is this valuable? Well, we've got increment and decrement, and the ultimate goal is going to be this up here, the modulus operator. To be able to implement modulus, we need one more mathematic operation. We're going to need subtract. So let's go ahead and implement subtract now. There is a way to implement subtract using recursion without saving any variables, and this is going to let us implement it in TypeScript. Let's just go and implement it in regular JavaScript for now, and then we're going to convert it over later. So I'm going to create a new function here called subtract, and it's going to take two values. N is a number, and then the amount we'd like to subtract, which is also going to be a number. So the way we're going to do this is using this very simple recursive algorithm. Let's say that n is 5 and amount is going to be 3. We're going to first kick this function off and call the value, and we're going to do a check, and we're going to say, is amount equal to 0? If it is, we're going to return n. If this is not true, we're going to recurse again, so we're going to call subtract in here, and we're going to decrement both of the values. So I'm going to decrement the first value, which is going to give us 4, and then I'm going to decrement the second value, which is going to give us 2. We have got decrement already, we've already defined that up here, so there's no problem there. Let's go ahead and quickly create one just to see if this is working. I'm going to call this one dec for now, just to keep it short and sweet. It's going to decrement a single number, and all we're going to do is return n minus 1. And that's going to get our decrement function working. So what's going to happen now if we do this? We're going to end up with n is equal to 4, and we're going to have amount is equal to 2, because we've decremented both of those. Again, amount is not equal to 0, so we repeat the process again. We now have n is equal to 3, and amount is equal to 1. Amount is still not equal to 0, so we're going to do it again. Now we have 2 and 1, and amount is finally equal to 0. And based on that, we're going to go ahead and return the n value. In this case, n is now equal to 2, so we're going to get our result. 5 minus 3 is 2. Let's go ahead and implement this in JavaScript, see it working, and then write the TypeScript type equivalent. So the first thing I'm going to do is jump in here and just say if amount is equal to 0. If it is, we're going to return n. If it's not, we're going to return subtract, and then we're just going to say decrement on n, and then we're going to say decrement on amount. With a bit of luck, this is going to work out of the box. Let's go ahead and give it a try. I'm just going to do a quick console login here to see if this is working. Pass in subtract 5 and 3, and this should give us 2. I'm just going to head over here and compile this and run it through Node.js, and it is working. We are getting 2, so everything is working as expected. 5 minus 3 is 2. Let's now go ahead and actually implement this using types. So what we're going to do is create a new type. I'm going to call this one subtract with 2 generic parameters, n and amount. It's going to be equal to a map, and I'm going to explain this in just a moment. We're going to have 2 conditions. Amount is equal to 0 or amount is not equal to 0. So if amount is equal to 0, we're going to say amount equals 0. If this is true, I'm just going to go ahead and return the number, n. If it's not, we're going to recurse. And that means we need to call subtract again, passing in decrement on the n value, and we're also going to say decrement on the amount value. Finally, let's go ahead and write a test and see if this is working. So we're going to have our test function. Again, it's an array with our test cases. It looks like I already declared a test function somewhere else. Let's go ahead and delete that one. I believe it's up here. So let's go ahead and assert that this is going to work. So what I'm saying is subtracting 2 from 5 should give us 3. So 5 minus 3 is going to give us 2. And this is actually not going to work because we've made a mistake. I intentionally made this mistake because I'd like to explain what's going on here. What we need to do is kick this off by passing in the initial value. So let's say we had a simple function or a simple variable called foo. It has 2 properties. We may have a, which is going to be a foo, and we may have b, which is going to be a bar. What we can do now is reference one of these using this operator with the square brackets. So for example, foo of a would give us foo, or foo of b would give us bar. And another way of doing that, instead of writing it like this, would be to inline it right here, a or b. And that's exactly what we're going to do with our subtract type to push the initial condition into the recursion. What I'm going to do is do that here. This is not an array of subtract. It's going to kick off the original recursion with the correct value. And we're going to check now if amount is equal to 0. So I'm going to see if amount extends 0, remembering that this is basically the same as saying equals in this context. If it is true, we're just going to say the amount is equal to 0. And that's just going to go ahead and return n. If it's not true, however, we're going to need to recurse. So let's just go ahead and recurse. And now our test is passing. Everything is working correctly. Let's just make sure it fails for the right reasons. For example, 5 minus 2 should fail. 5 minus 2, of course, is 3. That now passes, and this fails for the right reasons. Definitely a good place to be. So this is a little bit of a complex one. If you're not sure how this works, go ahead and write it out yourself. But just remember, this is not an array of subtracts. This is referencing one of the keys for the initial condition. Now that we have subtract, we're in a position to finally implement what we've been trying to do, which is the modulus operator. For example, 15 modulus 5 should give us 0, which means 15 is divisible by 5. We're going to again write a recursive function to do this. Let's go ahead and do that now. I'm going to call it is divisible by, and we're going to take 2 values. The first is going to be the number, which is going to be n, and the second is going to be the amount, that's also going to be n. And this is going to be very similar to the subtract one, but we're going to have an extra condition. So the first condition we're going to do is call this. Let's say we call is divide by, passing in 15, and let's say 5 is probably a good example. The first thing we're going to do is see if n is equal to 0. If it is, we're going to return true. So I'm going to say return true. If it's not true, we're going to check if it's less than 0. And if this is the case, it's going to be false. And we're going to explain this in just a moment. Finally, if neither of these is the case, I'm going to return this, and we're going to subtract amount from n. So it's going to give us 10 and 5 instead of here, because I'm subtracting 5 from 10. We're then going to repeat the process again by comparing these. Of course, n is 10 and it's not equal to 0 or less than 0. Going to repeat this again with 5, and that means we're going to be calling it with 0. And finally, 0 is going to satisfy this condition. We're going to return true. And this means that 15 is divisible by 5. Let's say we started with a different number. Instead of 15, we might have said 14. This would then give us 9, this would then give us 4, and this would give us negative 1. Negative 1 is less than 0, so it's going to return false. That's because 14 is not divisible by 5. So now that we have that, let's go ahead, implement it really quickly, make sure it works, and then change this to be a TypeScript type definition. First thing we're going to do is do that check on n. So if n is equal to 0, we're going to go ahead and return it. So I'm going to say return return true rather, because it is divisible by the number. If not, if it's less than 0, it means it's not divisible, so I'm going to return false. Finally, I'm going to fix this up really quickly. And now if neither of these is true, we're going to recursively call is divisible by passing in the difference between n and amount. So I'm going to say subtract n and amount, and then we're going to pass in the amount, which is not going to change. Let's just make sure this is working before we implement it with two very simple cases. The first is going to be 15 and 5. There we go. And the second is going to be 14 and 5. So we should get true and false. Let's go ahead and run this. True and false. So this is working correctly, exactly what we were expecting. Okay, so now that we have confirmed this is working correctly, we're going to translate this into a TypeScript type. Let's go ahead and create a new type. I'm going to call this one is divisible by. It's going to take two arguments. The first is going to be n, and the second is going to be the amount. And this is going to again use that kind of map trick to do the recursion. The first case is going to be if n is equal to 0. So we're going to say n is equal to 0. If that is true, we're just going to return true. Of course, if it's less than 0, we said it's not going to be divisible. We're going to return false. And as you might expect, we now have the recurse type. And we're just going to literally translate exactly what we have here into TypeScript. So I'm going to say is divisible by, pass in subtract with n and amount, and then we're just going to pass in the amount. Finally, we need to kick this off with the original condition, as we said before. Let's go ahead and do that. We're going to see if n extends the amount, or if it's equal to 0 in this case. If that is true, what we're going to do is just say n is equal to 0. Otherwise, we're going to go ahead and do another check and see if n extends nan. That means we've gone below 0, we're outside of our type system. If that's true, we're going to say n is less than 0. Finally, if neither of these is true, we're just going to go ahead and recurse. And this should hopefully be working. Let's go ahead and try it out. Going to create another test type in here. We're just going to assert that these are equal. And let's go ahead and make our divisible by 3, 5, and 15 types, since that's what we need for our FizzBuzz algorithm. I'm going to create a new type, isDiv by 3. And this is just going to be an alias to our isDiv by type, passing in the value of n, and let's say 3. Let's make this n in here, and with a bit of luck, this is going to work correctly. Is divisible by 3, and I'm going to pass in my number, let's say 6. It is divisible by 3. This one should be true, and that is actually working correctly. Let's see what happens if we make it fail. For example, if this is 5, it's of course going to fail. This is false, and now it is correct. So everything is working as we would expect. Let's go ahead and make the rest of our types. We're also going to have 5, which is going to be very similar. It's just going to be 5 here. And finally, we're going to have 15 as well. We can actually combine 3 and 5 for 15. So we're going to say is divisible by 15. And that's just going to be the intersection between both of these types. So we're going to say is divisible by 3, passing in n, and we're going to use the intersection operator to check if it's divisible by 5 as well. One common mistake I made when I was working on this was by using the union operator. What this means is any type that's divisible by this one or divisible by this one. More specifically, if we look at the diagram for the union operator, we can see that it is going to be any value that falls in any of these sets. What we really want for 15 is going to be a value that falls in between both of these sets, but does not include the external values. And that's going to be this intersection operator. So you must be both divisible by 3 and 5 to be divisible by 15. It is a little confusing because this normally would represent AND, but it actually has to be the intersection operator instead. Now that we have all of our divisible types, we actually have everything we need to implement our FizzBuzz. You can see up here, we have the divisible by 15, 3, and 5. And all we need to do is write a for loop. Obviously we haven't got for loops, but we do have recursion. And then we just need to go ahead and loop over our numbers and collect all the results in some kind of array. We haven't seen how we can store values yet. Let's go ahead and do that now. What we're going to do is write a new function called append. It's going to take two values, the new value, which we're going to store in the array, and the existing value, which is going to be a list. That's just going to extend a list of anything, because we need to store both numbers and FizzBuzzes, which are going to be strings. What this is going to do is use the parameters key, or the parameters type. I'm going to explain this one in just a moment. What this is going to do is extract all the parameters from a given function. What we're going to do is take this value, n, and this list, and we're going to merge them into a single value using a function. So I'm going to use a spread operator, spreading over the list of anything, and then I'm going to append the new value element on the end. And that's going to return anything. We don't care what it returns, we just care about the parameters. In this case, the list and the value. Up here we have two values, the value and the list, and now we have a single value down here, which is going to be all of these merged together. Unfortunately, this is not going to work. If we mouse over this, we can see a rest parameter must be the last in a parameter list, which is not what it's not going to work in TypeScript. What we need to do is move this to the end of a list, I'm going to go ahead and do that one. And now it's going to compile. However, we've changed the behavior now. Instead of putting the new element at the end, we're now putting the new element at the start. So we're going to have to change this to be prepend to be more accurate to what it's actually doing. Just to confirm what this is doing, parameters is going to return the inner values here. We've just got a single list here, and by using the spread operator, we're merging them all together. Let's go ahead and write a test to make sure this one is working. So I'm going to have a type of test, of course, with our test cases in here, and we're going to assert that if we have a list with nothing in it, and then we call prepend on a value of 1 to our empty list, this should give us a list of 1. And hopefully that's going to pass. It looks like it's not. I've probably made a typo somewhere along the line. Let's go ahead and figure out what's going on. So I'm prepending a value of 1 into this list, and that is actually failing for some reason. Have I made a typo, or have we actually got an incorrect implementation detail? I'm inclined to say that we have an incomplete implementation detail. Let's go ahead and rewrite this test just to see what's going on. I'm going to say my result here is just going to be equal to, let's say, the prepend value of 1 into an empty list, and we expect that to be a list of 1. So let's try again one more time. I'm going to say that a list of 1 should be equal to this result. That is still failing, so it looks like I've made a mistake somewhere along the line. It says here duplicate identifier result. I guess I've used this one before. Let's go ahead and update that, and this is now passing. What this means is I had a typo originally. This is getting quite confusing with all these recursive types, but you can see this is now passing. Everything is working as you would expect. To avoid making that mistake, I'm going to go and delete that other result type, which is here. Delete that one off, come back down here and change this to be result, and everything should hopefully still be passing. Let's make sure this is working with a regular string as well. So I'm going to say that we're appending to a different list. It's going to already contain A, and now this should give me a list of both 1 and A. So we're going to have A as the first value and 1, and that is working correctly. We're prepending this A value into this list of 1. Is that actually correct? No, it should be the other way around. We're prepending the A value, or the 1 value, sorry. So this should be A. And our test was failing for all the right reasons. Again, prepending really not the best thing to do. I would much rather append, but this is one of the limitations of TypeScript's type system. Anyway, let's go ahead and continue writing. We now have the ability to save all of our list numbers, so we should be able to iterate over everything recursively and build our list. Because we have prepend instead of append, instead of doing something like this, where we iterate from 1 up to n, appending each of the numbers, we're going to have to go the other way, 16 iterating down to n and prepending the numbers. It is going to give us the same result, it's just a bit more difficult to think about. Anyway, let's go ahead and try it out. I'm going to create a new function here called getValue, and this is going to get the correct FizzBuzz value for a given number of n. So let's go ahead and try this one out. Just going to delete that test for now. And what this is going to do is check if it's divisible by 15 first. So we're going to say if n, or rather is divisible by 15, n extends true. So if this statement is true, we know it must be divisible by 15. So what we're going to do is return FizzBuzz as the spec specifies. I'm just going to go and grab the result so we can remember what this is supposed to do. We should be returning fizz for 15. We should be returning FizzBuzz for 15 rather, fizz for 3, and buzz for 5. So if this is not correct, we're going to keep on checking. Let's see if it's divisible by 5, passing in n. If this extends true, it is divisible by 5. And what that means is we're going to return fizz. No, it's not. It's actually going to be buzz. What a silly question. Anyway, now that that is working, we're going to do the final check, which is going to be divisible by 3. If this one is true, we're going to return fizz. Finally, if none of these are true, it means it's not divisible by anything. We're just going to return n. Now that we have that, let's go ahead and write our final recursive function. What we're going to do is loop over each number, starting from 16 down to 0, collecting each of the FizzBuzz values as we go. For that reason, I'm going to create a new function called FizzBuzz of n. And we're going to also pass in a list of results, which is going to be called output. And this is going to, again, use that trick with the map and passing in the initial value to kick off the recursion. We're going to have 3 conditions in here, or actually we're going to have 2. We're going to see if n is equal to 0, n equals to 0 rather. That means we've finished all the recursions. All we're going to do is return the output list by saying output. Alternatively, if we're still iterating, we're going to just say recurse as you would expect, and then we're going to just call this function recursively until n becomes 0. That means we're going to have to make sure we decrement n each time we loop over it. So I'm going to jump in here and do FizzBuzz again. The first value is going to be n, and we need to make sure we decrement that to be able to get down to 0, or we're going to recurse forever. The next thing we need to do is the output, and that's going to be our list. So we're going to prepend to the output. The first argument is the element we're pushing in, which is going to be the get value for the current n value, and then we're going to pass in the output here as well. And that should be all we need to do. We are getting an error here. It's saying that we haven't got a list probably, so we're going to have to say that this does indeed extend any, which is going to give us our list and get this to compile. Finally, we need to do our recursive condition. So let's go ahead and see if n is 0. So we're going to see if n extends 0. If this is correct, we're going to say n is equal to 0. That is going to give us our result. If this is not true, we're going to go ahead and recurse. So we're just going to put in recurse. And this should be all we need. Let's go ahead and try it out. I'm going to do a type of result is equal to FizzBuzz for, let's say, 5. And if we have done everything correctly, we should hopefully get something working here. We do have an error. It's saying that generic FizzBuzz requires 2 arguments. We need an array to collect everything. And if we mouse over this, we're getting another error saying we've used result again. I'm just going to delete that one. Finally, our errors are gone. And if we mouse over this, it is actually working correctly, well, kind of. You can see if we mouse up here, we have the first element is going to be 1, which is incremented from 0. We then have the double increment for 2. We have fizz. We have the quadruple increment for 4. And we have element 5 being buzz. This is pretty unreadable, but everything is indeed working correctly. Just to really validate that, we're going to write a quick test, and then we're going to try and improve that output a little bit. So what I'm going to do is assert in here that equal is actually equal to what it should be. So we're going to say result should be equal to a 1, 2, a fizz, a 4, and a buzz. And that is actually going to compile. Everything is working correctly. So this is doing what it's supposed to be doing. What would be really nice is if we could actually see the numbers in here instead of increment, and that's exactly what we're going to do right now. What I'm going to do is replace my number system with real numbers and see if that works. Let's jump up here and do that now. The reason we can't see the numbers is we haven't got numbers. We have abstract types that represent numbers, offset from a generic base type, but we haven't actually got numbers. We can, however, create some by hard coding it. So let's go ahead and update our increment and decrement functions to reflect real numbers. What we are instead going to do here is change how these work. Increment is actually going to be a full list. So let's go ahead and create a new type. We're going to start from, let's say 1, and we're going to go all the way up to 15, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. It is somewhat critical I don't make any mistakes here, because if we do, we're not going to have a valid type system anymore. And we need to now go extract the correct value. I'm going to explain this one in a moment as well, and it's going to be cast as a number. The next thing we need to do is do decrement as well. It is going to be quite similar. We're just going to replace this one by commenting out our original decrement function and updating it with increment. It's actually going to be very similar to increment, so I'm going to copy it. The only difference here is you can actually decrement below 0, below 1 rather, you can have 0, and you can also have nan. And that hopefully is all we need. How this works is it's actually just referencing an array. So we have an array here with numbers from 1 to 16. Passing in the value here is going to cast this into a number. So let's say you pass in 1, or you pass in 0. The 0th element is going to be extracted out, and it's going to give us the 0th element of this array. In this case, it's going to be 1, and so on and so forth. We have exactly the same thing with this. It's just going to start from nan. This is a little bit confusing again, but it does work, and this is how it's going to be done correctly. So for example, here we have increment of 0. It's going to be incrementing the 0th value, which is going to be cast to a number up here, and that's going to give us the 0th element, which is going to be 1. Anyway, the whole point of this is we're able to correctly get our output improved and more pretty. Let's go ahead and see if it actually worked. By scrolling down here and observing we actually have an error here, kind of weird, but we're going to ignore that one for now, see if the result is correct. And so it is. We're actually getting our numbers all the way up to where we would expect. Actually, no, we're not. We've got a bug somewhere along the line. So we have element 1 can be 1, fizz, buzz, or fizz. That's obviously not correct. I think we've made a mistake with our numbers somewhere along the line. Let's go ahead and see if we can figure out where that's happening. I'm going to check these numbers just to make sure I haven't made a mistake. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And we have nan 0, 1, 2, 3, 4, 5, 7, 8, 9, 10. This actually all looks correct to me. I wonder if we need to pass in that extra number on the end for 17 and 17. Let's see if that has fixed our error. Jump down here, and we are getting the correct result there. So it looks like I didn't have enough numbers. We were actually somehow getting to a point where we were recursing outside our system and getting some kind of nan value reference. That is not the case anymore. And with a bit of luck, I can actually put 16 in here and get a correct result. 16.17, that's definitely not what I was hoping for. Let's try 15. That is much more valid, and that is exactly what I was expecting. You can see the original result, or the goal on 110 is going to be 1 all the way up to 16. We're getting to 15, it's pretty close. We probably need to extend our numbers a little bit, but this is enough for now. 1, 2, fizz is correct, we're getting our buzz, and more importantly, 15 is FizzBuzz, exactly what you would expect, so this is working correctly. It was a bit of work and we saw a couple of TypeScript tricks along the way, but we did manage to implement FizzBuzz using types only, which is pretty interesting. Again, there is a full post here by Gal Schlesinger. You should definitely check this one out for a more concise explanation and see how it works, but the ideas are very much the same. Let's quickly review what we have learned. So we saw we were able to create our own type system by using increment and decrement, creating that relationship by using increment. We also saw a number of very useful keywords such as extends to create that relationship between the A and the B variable. We saw how you can use recursion to create a kind of for loop in TypeScript. And we also saw how to use the infer keyword, which has since been deleted. There it is, which is allowing you to infer a type given another type. Finally, we saw this kind of trick down here with the key value map, where you're able to actually implement that recursion for TypeScript as well. And we also saw how you're able to save values by using this prepend value here, or this prepend type. What this actually shows is you can do recursion and you can also store values, which is two of the things that make a system Turing complete. Something I'll definitely discuss in a future video. Anyway, I think this one's more than long enough. Definitely pull this code down and try it out yourself and experiment. It does take a bit of time to get used to this very abstract mode of thinking, but it's definitely worth it. It allows you to write more flexible types, and thinking in this abstract manner is just a really rewarding and satisfying experience. Anyway, I think that's enough for now. I'll see you in the next video.